There are 4 definitions of the mole. Your textbook mentions that the SI unit of the amount of substance is designated by the unit called the mole. So we quantify in chemistry how much of something we have using the unit mole. This is the term, or the unit, but it has an abbreviation MOL. Just like kilograms is abbreviated kg, and pound is abbreviated lb, the mole has an abbreviation of MOL. There are 4 definitions of the mole that you should familiarize yourself with and be able to use them interchangeably depending on the need and the type of problem that you will encounter. So the first definition of the mole is 1 mole is equal to Avogadro's number of molecules, ions, or atoms. So 1 mole is going to equal to Avogadro's number of molecules, ions, or atoms. Avogadro's number is a constant, and that constant is 6.0223 times 10 to the 23. I'll write that down here. It's probably a number that you should just go ahead and memorize. And again, that's 6.02 times 10 to the 23 molecules, 6.022 times 10 to the 23 atoms, or if you're dealing with a substance that is an ion, a charged particle, it could be ions. So here, conversion factors are going to be important. If I have 1 mole of the molecule CO2, that also means I have 6.02 times 10 to the 23 molecules of CO2 in that 1 mole of substance, CO2 gas. If I have 1 mole of iron, the element in the periodic table, I'll have 6.022 times 10 to the 23 atoms of iron. If I have 1 mole of carbon from the periodic table, that element, I'll have 6.02 times 10 to the 23 atoms of carbon. These are all called conversion factors. And you may remember from high school, you can use these conversion factors to go from molecules to moles, or whatever you need to do to cancel out the units to get your desired units. So, since these are conversion factors, I could just as well write 1 mole of Fe in the numerator, 6.022 times 10 to the 23 atoms of iron in the denominator, but I could also flip this around, depending on how I want to cancel my units. So the conversions are going to be the same. 6.022 times 10 to the 23 atoms of iron are found in 1 mole of iron. So it also works for ions. So I could have 1 mole of calcium ion. The only difference between calcium ion and iron, or calcium ion and carbon, is that this is an ion, and this is elements from the periodic table. So I will designate this as 1 mole of calcium ion as 6.02 times 10 to the 23 ions of calcium. So again, the focus is on conversion factors and being able to use these conversion factors. Be prepared to flip them, have the whatever is in the numerator be in the denominator, and have whatever is in the denominator be in the numerator. Be able to have that flip for your convenience if you want to get units to cancel each other out. We use these for basically converting. So that's the first definition of the mole, Avogadro's number of subatomic particles. The second definition of the mole is the part-whole relationship of a compound. So here we go again with our conversion factors. Let's go back to our example of CO2. 1 mole of CO2 consists of 1 part carbon and 2 parts oxygen. So 1 mole of CO2 has within it 1 mole of carbon. Now I could flip this and say for every 1 mole of carbon in the numerator, there's 1 mole of CO2 in the denominator, again to cancel out the units. 1 mole of CO2 will have 2 moles of oxygen. That 2 comes from the fact that we have 2 atoms of oxygen in 1 CO2 molecule. So you can use this as sort of a ratio. Let's have another example of water. 1 mole of water will have 2 moles of hydrogen, or 1 mole of water would have 1 mole of oxygen. You could take something that's even more complicated like glucose. Glucose has this structure, C6H12O6. So it's a purely covalent compound. Carbon and hydrogen and oxygen are all nonmetals. So what are the ratios that can be determined from here? So here I'll just have 1 mole of C6H12O6 in the denominator, knowing that I could also put it in the numerator. And for every 1 mole of this glucose molecule, I can have 6 moles of carbon. Here I'll just put this in the numerator, 1 mole of C6H12O6. I have, what other relationships do I see? I'll have 12 moles of hydrogen. And I'll have this now, instead of it being a numerator, I'll follow this rule and have the glucose molecule in the denominator. Every 1 mole of C6H12O6 glucose, I can have 6 moles of carbon. So that's the part-whole relationship. And the third definition of the mole is the moles are a coefficient of a balanced chemical equation. So you have to balance chemical equations. And once you balance the chemical equations, that number that's in front of the reactant or the number that is in front of the product is a mole by mole ratio. So let's take an example. Glucose, as we've seen before, is C6H12O6. It can actually combust or react with oxygen gas. I'll make this glucose in water. And that combustion reaction generates carbon dioxide and water. Water is going to be a liquid. Carbon dioxide will have the state of a gas. So if you balance this chemical equation, I'll just go ahead and balance it for you. We have 6 moles of oxygen here. That is the stoichiometric coefficient. We have 6 moles of carbon dioxide here. That is its stoichiometric coefficient. And we have 6 moles of H2O here. So you can go ahead and check it, and you can see that we have 12 hydrogens, 6 carbons, 6 carbons. 6 plus 12 is 18. And the reactant side, 12 oxygens plus 6 oxygens is 18. So my reactant side atoms balances out my product side atoms. So the third definition of the mole comes in where we can take the balanced chemical equation and do a mole by mole ratio. So what are some of the relationships that can be generated from this mole by mole ratio? Well, let's see here. There's several. For 1 mole of C6H12O6, there is 6 moles of oxygen. That's 1 mole of this to 6 moles of that. Flip this dependent upon what I need to do to get my units to cancel out. What's another one? Here's the stoichiometric coefficient 6 in front of the CO2. So for every 6 moles of CO2, I can have 6 moles of oxygen. That actually cancels out to 1 to 1. What about another relationship? How about the relationship between this glucose and that water? So I'll have the water in the numerator, 6 moles of water. For every 6 moles of water, how many moles of glucose are there? 1 mole of glucose. And you can think of just several of these types of examples. Okay, you can do this within the reactant side, as in here, or you can go from reactants to products, as in here. It really doesn't matter. The only important thing is that the equation has to be balanced. So using this mole-mole relationship, you can be able to do a lot of important things. Particularly, the most important thing is stoichiometry. And that can only be done if you know this third definition of the mole, that the coefficients of the balanced chemical equation can be used for a mole-to-mole ratio. The fourth and final application of the mole is just as important for stoichiometry, and that is the mole is the molecular weight of a substance in grams per mole. Now, it's very important that you know the units here. The units are in grams per mole. So 1 mole of a substance has a certain number of grams. Now, where do we get those grams? We get them from the periodic table. Remember the lecture on the periodic table? The molar mass is in grams per mole. So let's go back to our CO2 example here. For every 1 mole of CO2, how many grams are in 1 mole of CO2? Let's get our periodic table out. Always consult your periodic table. Well, 1 mole of CO2 has 1 carbon atom. So that 1 carbon atom has a molecular weight of 12.01. And that's carbon. And 2 oxygen atoms. Oxygen has a molecular weight of 15.99. So I'll just call it 16.01. And you have to multiply it by 2 because you have 2 oxygen atoms. Now, when you get really good at this, instead of using 15.99, I just go ahead and say 16.01 because I've come to the point in my life where I don't consult the periodic table. I just know carbon is 12 and oxygen is 16. And so I just say 12.01 and 16.01 as carbon and oxygen respectively because the 0.01 comes from the fact that we do have some isotopes. So when you get really good, you can just memorize some of these off the top of your head. So 12 plus 16 times 2, well 16 times 2 for the oxygen is actually 32.1 or so grams, and 12.01 grams for the carbon. And be aware you have to multiply oxygen by 2 because you have 2 moles of oxygen. And adding that up gives you 44.01 grams, or here 44.02 grams. I'll just keep it 0.01 grams. So 1 mole of carbon dioxide has 44.01 grams. When you get really good at it, you can just flat out say 44.01 grams. You can put 44.02 grams. It's going to be a very, very small difference in your answer in terms of your decimal rounding. So because a lot of these molecular weights in the periodic table are decimals due to isotope abundances and rare isotopes that actually contribute towards this atomic mass number, you can just go ahead and round, and I usually like to do that. So as you become more experienced, you can just put out these numbers right on top of your head. Let's do one more example here. Glucose. Okay, glucose is C6H12O6. So what is the molecular weight of glucose? Or 1 mole of glucose contains how many grams? Well, I have 6 carbons, so I know that the molecular weight of carbon is 12.01, so that's going to be 72 grams. Notice I'm doing this on top of my head, and you'll get to that point with enough practice. So that's my carbon. Hydrogen is 12, so 12 times 1.01, so that's about 12.01 grams. And then oxygen is, I have 6 of those, and 6 oxygens has a molecular weight. Each oxygen has a molecular weight of 16.01, so that is going to be 96.01 grams. So you can use your periodic table to look at the molecular weights. And with enough practice, you should be able to do this. Never memorize this. Okay, I've just been doing this for so long, and you will be doing it for so long, especially your chemistry majors that become juniors and seniors. You'll be doing this so long that you can just recite these numbers off the top of your head. And when you add all these up, you get 180, and I'll just do a rounding of 0.01 grams. So for every 1 mole of C6H12O6, that 1 mole contains 180.01 grams of glucose. The rounding is good enough for our calculations here. Just as equivalent, 180.01 grams of glucose are found in 1 mole of glucose. Okay, again, just want to emphasize that you can flip these depending on what you need to do to get your units to cancel out. Let's do one more. Let's do sodium chloride, which is table salt. Table salt is NaCl. So you can go to your kitchen and weigh out some table salt, which is essentially sodium chloride. But if I tell you to weigh out 1 mole of it, how much are you going to weigh out? all you have to do is add the molecular weights. So sodium, this I don't have memorized. Sodium is going to be about 22.990 grams, so I'll just call it 23. Now you can use 22.990 grams. That's fine. Perfectly all right with that, because the final answer you get versus the final answer I get is just going to be slightly off by in maybe the 10th or 100th decimal place. CL, what is CL? CL is 35.5453. I'll just call it 35.01. But you guys can just put in the exact number, 35.453, if you want to get it a little bit more accurate than my answer. And 58.02 grams, 58.01 grams, that's fine. So if I want to give you 1 mole of sodium chloride, what do? I have to go grab the sodium chloride, go to my bench, weigh out 58.01 or 58.02 grams of sodium chloride. If I give you 58.02 grams of sodium chloride, I'm essentially giving you 1 mole of sodium chloride. So the molecular weight is a crucial aspect of your definition of the mole. Now, units, 1 mole of sodium chloride has 58.02 grams of sodium chloride. So units are going to be grams per mole, but if you need to get your units to cancel out, you can flip it to get moles per gram. 4 definitions of the mole. The first one is its Avogadro's number of species, molecules, ions, or atoms. The second definition is the part-whole relationship. So for example, here in 1 mole of sodium chloride, I'll have 1 mole of sodium. How many moles of chloride will I have in 1 mole of sodium chloride? I'll also have 1 mole of chloride. The third definition is the coefficients of a balanced chemical equation. And the fourth definition is the molecular weight. So we figured out the molecular weight of sodium chloride, glucose, and all you have to do is just add up the molar masses that are found in the periodic table. And I just want to say we're talking really here relationships between the balanced chemical equations, relationship between moles and grams of a substance according to the periodic table, relationships according to the part-whole, and relationship according to Avogadro's number. So let's look at the first problem here. Calculate the molar mass of HNO3, potassium bicarbonate, which is KHO3, and nickel 2 nitrate. So the molar mass, molar should bring up the term mole, and mass tells you that it's going to be in grams per mole. So nitric acid is HNO3, and I can't emphasize this enough. Nitric acid is going to be HNO3. I really can't emphasize this enough. The units, okay, the units are going to be in grams per mole. The molar mass has units of grams per mole. Those are the correct units. If you don't put the correct units then and just put in any number, that's just a wrong answer. A number without units is meaningless. So let's count this up here. So go back to our periodic table. Never forget your periodic table. H has an atomic weight of 1.00794. I'll just go 1.01 here. Nitrogen has an atomic weight of 14.007, so I'll just go 14.01. And oxygen has an atomic weight of 15.99. I'll just call it 16.01. But, okay, so don't get fooled by this. We have 3 oxygens, so 3 times 16.01. And units are grams per mole. Also, the units are going to be very important. So if you do all of that, 1.01 plus 14.01 plus 3 times 16.01, you do all of that addition, I'm getting 63.02 grams per mole. So for HNO3, it's going to be nitric acid, 63.02 grams per mole, and units. That's all I can say here. For molar mass, the units are going to be in grams per mole. What about potassium bicarbonate? HCO3. Pretty much the same situation. What is potassium? Potassium is 39.098, so I'll just go 39.098, so maybe I'll just go 39.09. H is going to be 1.01, and carbon is going to be 12, so I'll just call that 12.01. Use your periodic table. Use it, and then oxygen, so there's your carbon at 12. Your oxygen is going to be 15.99, so I'll just call it 16.01. Now, I'm rounding. You can use the exact numbers that are listed in your periodic table. You'll get a slightly different answer, but it's going to be very, very close and essentially the same. So 9.09 plus 1.01 plus 12.01 plus 3 times 16.01. Okay, this comes from K, this comes from hydrogen, this comes from carbon, and these come from the 3 oxygens that are in the formula for potassium bicarbonate. Potassium bicarbonate, I got a molecular weight of 100.14 grams per mole, 0.14 grams per mole. Again, be cognizant of your units. All right, the next one is nickel 2 nitrate. Notice how nickel has the Roman numerals attached to it. That has to do with nomenclature. Transition metals have their charge denoted by Roman numerals. Okay, because nickel is a transition metal in that system devised many years ago, transition metals, their charge is given by a Roman numeral. So nickel 2 nitrate, that will be nickel. So I definitely do not have nickel memorized, so 58.693, I'll just say it's 58.70 for nickel. All right, so nickel nitrate, how many nitrogens do I have here? All right, it's not one nitrogen. That nitrate is all part of that 2, okay? So that nitrogen is twice, so it's going to be 2 times N. And N, we said, was 14.01. And what about oxygen? You have 3 oxygens, but you have 2 nitrates. Okay? So if you go back to nickel 2 nitrate and its formula, we know nickel is plus 2 because it tells us that. Nitrate is a polyatomic ion that we should memorize from our flashcards, and that has a charge of -1. That whole thing has a charge of -1. So N, the 3 oxygens, that whole thing has a charge of -1. For ionic compounds, you do the switcheroo, and that formula is going to be Ni parentheses NO3 2, because the NO3 is one whole independent unit. That whole thing gets to 2 when you do the switcheroo for ionic compounds. So 2 nitrogens, and you're going to have 6 oxygens. So 6 times 16.01. And that will be the answer in grams per mole. I got 182.78 grams per mole. That is the molecular weight. So if I had nickel 2 nitrate in the lab and I weighed at 182.78 grams of that substance, that's essentially 1 mole of that substance that I have in my dish. The second problem here, mercury 2 bromide, here is its chemical formula, weighs 8.65 grams. So you have 8.65 grams of this substance known as mercury 2 bromide. How many moles are in this? All right, so if we have 8.65 grams of mercury 2 bromide, I know that for every 1 mole of mercury 2 bromide, I have how many grams of mercury 2 bromide? That is the relationship here, the molar mass relationship. So mercury in the periodic table has a molecular weight in grams per mole of 200.59. So I have 200.59, and I have 2 bromines. So 2 times bromine is 79.904. So 79.904. I'll just say 79 point. I'm rounding, but I got my main numbers in, so that's okay. This whole thing Addition is the molecular weight of mercury 2 bromide in grams per mole. So let's do that math. 360.39 grams per mole. But here I've switched the relationship, so instead of grams per mole, have moles per gram. Remember, in conversion factors, you can flip the numerator and denominator. The reason why I flipped this and went moles to grams is because I can cancel out the grams and grams. So canceling out the grams of HgBr2 with the grams of HgBr2 here in the denominator, that's why I put this in moles to grams, that relationship. The units cancel out, and my final units are going to be moles of mercury 2 bromide. And so 8.65 divided by 360.39, again, units. Good practice for whatever field you want to be in, requires conforming to the etiquette, and it's good etiquette to put a number with units by it. So this relationship is part of the definition of the mole. Okay? 1 mole of a substance is the molecular weight of the substance as determined by summing up the molar masses in the periodic table. Third problem asks us for the mass of 0.45 moles of ammonium sulfate. Okay, so this is an ionic compound. Ammonium is a polyatomic ion you should know from your flashcards, has this formula. Sulfate is a polyatomic ion that you should know from your flashcards that has this formula. For any ionic compounds, we do the switcheroo, and we get NH4. Now that NH4 is one independent unit, that is one group, so that 2 goes for that whole NH4. This SO4 has that plus 1 unit, so 1 SO4 for 2 NH4. It's an ionic compound. You just have to memorize that NH4 plus is ammonium ion and SO4 minus 2 is the sulfate ion. Now we have 0.45 moles of this stuff. So if I have 0.45 moles of ammonium sulfate, grams of that substance do I actually have? Well, here we have relationship where for every 1 mole of ammonium sulfate, grams of ammonium sulfate are there. Well, you'll have to look it up in your periodic table. So 1 mole of ammonium sulfate consists of 2 moles of nitrogen. So 2 times N, 8 times H, 1 times S, and 4 times O. So oxygen is, or nitrogen, excuse me, nitrogen is 14.007. So 2 times 14.01. Hydrogen is 1, so 1.01. Sulfur is 32.066, so I'll say 32.07. And oxygen is 15.99, I'll just say it's 16.01. So if you do all of that math, then you'll be able to get the molecular weight of ammonium sulfate for 1 mole of that substance. When I did all this math, I got 132.21 grams. For every 1 mole of ammonium sulfate, I have 132.21 grams of ammonium sulfate. Here in this problem, the relationship is moles per gram. Here, for ammonium sulfate, this specific example, I flipped it to get grams per mole. So here, 1 mole of mercury 2 bromide is 360.39 grams of mercury 2 bromide. In this problem, there's 132.21 grams of ammonium sulfate in 1 mole of ammonium sulfate. This relationship and this relationship are the same. The only difference is I flipped the numerator and denominator, and that is convenient for me here because I can cancel out the moles of ammonium sulfate. And if I do 0.45 times 132.21 grams, my answer is going to be in units of grams of ammonium sulfate, which is what the problem is asking for. So 0.45 times 132.21. This is in 2 sig figs, so let's just call it, to make it in 2 sig figs, 60. On a test or an exam, I will just tell you, put it in 2 sig figs or round your answer to 2 decimal places. So I'll be more explicit and specific in terms of your rounding for your answer. All right, so It looks like I crossed out some of this one. Let's read it here together. How many molecules are contained in 6.53 moles of nitrogen gas N2? So nitrogen gas exists as diatomic, and it's asking for how many molecules. So what definition of the mole should you use here? You should use Avogadro's number. So 6.53 moles of N2 gas. That for every 1 mole of N2 gas, we have 6.022 times 10 to the 23 molecules. And 1 mole of N2 cancels out with the mole of N2 here. And if you do 6.53 times 6.02 times 10 to the 23 molecules of N2, your answer is going to be in molecules of N2. So to do that on your calculator, we will do 6.53 times, I'm going to put a parenthesis here, 6.022. I'm going to hit the exponent key on my calculator, the exponent key. 6.022 times 10 to the 23, so 6.022e 23, close my parentheses, hit my equal sign, and I'll get the answer of 3.93 times 10 to the 24. I'll put it to 3 sig figs. So 3.93 times 10 to the 24 molecules. 0.93 times 10 to the 24 molecules. Now, you're going to have to put the units. You can't just write it like this. It's asking for how many molecules, and you have 3.93 times 10 to the 24 molecules. More specifically, molecules of N2. Okay, so don't forget that as well. An interesting problem here is asking for us to calculate the mass of calcium sulfate, but the percent composition by mass. So all percentages add up to 100%. So it's like cutting a pizza. Okay, if you take a pizza slice out, you don't have 100%. But if you join all those pizza slices together, you still have 100% of the pizza. So all of this has to add up to 100%. But we also have to ask ourselves the question, how do we calculate percent composition? So like any percent, it's a part divided by the whole. So what is the whole thing? The whole thing is calcium sulfite. I'm going to do part over whole in terms of mass because it's asking for the percent composition by mass. So what's the total mass or the molecular weight of calcium sulfite? So it's calcium plus S plus 3 oxygens. So calcium is about 40 from the periodic table. Sulfur is 32 from the periodic table. Oxygen is 16 from the periodic table. So if I do get the total weight of calcium sulfate. So doing that summation, so I get 120 grams calcium sulfite. Now out of that 120 grams, how much of it is calcium? Okay, so I have 40.01 grams of calcium. That's my part. What's my whole? My whole is 120 grams of calcium sulfite. So in 120 grams of calcium sulfite, I'll have 40 grams of this. So 40 divided by 120, it's a percentage, so I'm going to have to multiply it by 100. It's going to be 0.33 times 100 would give it 33%. 33% calcium. What about sulfur? I have 1 mole of sulfur in 1 mole of calcium sulfate. So 1 mole of sulfur contains 32.01 grams of sulfur, and that's the part. The whole is 120 grams of calcium sulfite. So what's 32 divided by 120 grams? And that's 0.26. I multiply it by 100. 26%. It's actually 0.266666, so I'll just round it off to 27%. So I have 27% sulfur. And how much oxygen do I have now? All right, so I have 3 moles of oxygen for every 1 mole of calcium sulfate. Moles of oxygen gives me 48.01 grams of oxygen. It's 3 oxygen, so I have to multiply 16 by 3 to get 48. That's my part. My whole is 120 grams of calcium sulfite. So what's 48 divided by 120? It's 0.39999. I'll round that up to percent when I multiply it by 100. 40% oxygen. 33% of calcium in calcium sulfite, 27% sulfur in calcium sulfite, and 40% oxygen in calcium sulfite. If I sum all those up, I get 33 plus 27 plus 40, it's 100%. So I have reconstituted the whole. So this definition of the mole is using part-whole relationship. Part calcium, whole thing calcium sulfate. Part sulfur, whole thing calcium sulfate. Part oxygen, we have 3 oxygens divided by whole thing calcium sulfate. I multiplied by 100 to get this into percentage. When you get a percentage, you're essentially extinguishing the units because it's a part and a whole. So, the pizza analogy still holds forth. If I have 1 slice of pizza and I cut that pizza into 8 slices of pizza, the slices and slices of pizza cancel. And by taking that slice of pizza, I have taken 1/8 of that pizza, or I've taken 12.5% of that pizza. So a percentage basically removes the units because it's a percent. It's really a ratio. How much of that part did I take out or did I remove from the whole? Same thing with a chemical formula and the application of the mole. Here's a very good problem. It's called the empirical formula, and you'll encounter this a lot in other chemistry classes, and it's a good question that can be posted on a lab, an organic or an exam or a quiz. An organic compound is analyzed and found to contain 51.9% carbon and 9.8% hydrogen and 38.30% chlorine. So what is the empirical formula of this compound? Let's define the empirical formula. The formula is defined as the lowest ratio of all the atoms of the compound in the element. So lowest ratio formula. To our glucose example, C6H12O6 is not the lowest ratio of these numbers. The lowest ratio of these numbers is if you divide everything by the lowest common denominator, and that is 6. The actual empirical formula of glucose is CHO. But that's not really how glucose is. Glucose is C6H12O6. That's the molecular formula. But if you want the lowest ratio formula, then for glucose, it's going to be CHO. So it's asking for the lowest common denominator between the formula that contains carbon, hydrogen, and chlorine. And it's 51.90% carbon and 9.8% hydrogen, 38.3% chlorine. First thing I like to do when I tackle these types of problems with percentages, okay, this is a part-whole relationship. You want to make sure all of these percentages add up to 100%. And when you do that, they actually do add up to 100%. So if they add up to 100%, then basically I can say that I have 100 grams of a substance. And if I have 100 grams of this whole substance, it means that I have 51.90 grams of carbon. Convert that to moles. For every 1 mole of carbon, I have 12.01 grams of carbon. I have 9.80 grams hydrogen, and we know that for every 1 mole of hydrogen, we have 1.01 or so grams of hydrogen. And if I set the total mass as 100, I'll have 38.30 grams chlorine, and I know that for every 1 mole of chlorine, I have 35 or so. Let me look this up in the table. According to the periodic table, 35.45 grams of chlorine. If all these things add up to 100%, then I'll say I have 100 grams of it. And out of that total 100 grams, I have 51.90 grams of this, 9.80 grams of H, and 38.30 grams of Cl. So let's convert this to moles. It's always safe, and if you're stuck on a problem, just go ahead and convert it to moles and see what you get and see where to go from there. So converting these to moles, I have 4.32 moles of carbon, 0.80 moles of chlorine. So let's look at our chemical formula. It has C with 4.32 moles of that, H with 9.70 moles of that substance, and H, and then Cl with 1.080 moles of that substance, which is Cl. So this cannot be a formula. You cannot have decimals or fractions in any formula, whether it's the empirical formula or the molecular formula. So you will do your lowest common denominator. The lowest common denominator is achieved by dividing everything by the lowest number. Number here is 1.80, so that cancels out Cl. So I've normalized the Cl. 9.70 divided by 1.080 is 8.9, but I'm going to round that off to 9. Okay, so you can round up because you want a nice whole number here. You can't have 8.9 in your formula. 4.32 divided by 1.080 is, that in my calculator is exact at 4. And you cannot reduce this anymore. Okay, 4 cannot go to 9, and that cannot go to 1. Okay, you cannot reduce this. There's no lowest common denominator. Here is your answer, C4H9Cl. 8.4 grams of O2 gas. And for every 1 mole of O2 gas, there's going to be 32.01 grams of O2. Okay, it's 2 times 16. 2 times 16. It's not, okay, you can't just use straight up the multiply by 2 because you have 2 moles of O2 here. And we now know that for every 1 mole of O2, we have 6.02 times 10 to the 23 molecules of O2. Now I have extended this train. So now we have one conversion factor from one of the rules of the mole, and we have a second conversion factor. The grams and grams of oxygen cancel, the moles and moles of oxygen cancel, and I'm left with the units that I desire, molecules of O2. So 28.4 times 6.022 times 10 to the 23. Take that product and divide it by 32.01. 28.4 times 6.0, let me do this again here. 28.4 times, I'll do a parentheses, 6.022, get that exponent there. 23, close the parentheses, I get that, I divide it by 32.01 grams, and I'll have 5.34 times 10 to the 23 molecules of oxygen. Sure, you put in the units there. Now, how many atoms are actually there? All right, so one molecule of O2 actually contains not one atom of oxygen, but 2 atoms of oxygen. In our stoichiometric train, we know we have 28.4 grams of O2. We know that for every 1 mole of O2, it's 32.01 grams of oxygen. And now, what will our conversion factor be for this time around? Okay, for every 1 mole of O2, I actually just have 1 mole of O. I'm sorry, I have 2 moles of O. For every 1 mole of O2, I have 2 moles of O. And for every 1 mole of O, there are 6.022 times 10 to the 23 atoms of O. So Here is one definition of the mole, molar mass, used as a conversion factor. Here's another definition of the mole, part over whole, used as a conversion factor. Here's a third definition of the mole, Avogadro's number, used as a third conversion factor. Look at my units. Grams of O2 cancel with grams of O2. Moles of O2 cancel with moles of O2. Moles of O cancels out with moles of O. And now I'm left with atoms of O. So 28.4 times 2 times Avogadro's number, and do all of that divided by 32.01, and you should get double this. And the answer is double that, 1.07 times 10 to the 24 atoms of oxygen. Okay, notice the unit, atoms of oxygen. Sand and salt is 48% sodium chloride by mass. So if I were to draw this, here is sand, here is salt, and I have 48% sodium chloride, which means I have 48% grams of sodium chloride. And how many grams of sand would I have? Just make your life easy and pretend you have 100 grams of this substance. So that would mean I have 52 grams of sand here. Okay? So give a nice round number of 100 and you'll have 48 grams of sodium chloride, 52 grams of sand. That is essentially 48%, which is 48 grams of sodium chloride in 100 grams of mixture. Okay, and what is my mixture? Sodium chloride and sand. So that would be the proper conversion factor to use. You're asked for how many moles of sodium chloride are in 74 grams of this mixture. So 74 grams of the mixture. The mixture is sand and salt. Well, we know that in every 100 grams of mixture of sand and salt, I have 48 grams of sodium chloride. Okay, that is essentially 48%. Okay, 48 divided by 100, multiply that by 100 to get 48%. And we know that for every 1 mole of sodium chloride, how many grams of sodium chloride are there? Okay, well, sodium, looking at my periodic table, is about 23. And chlorine is about 35. So I'm just using my head here. So 58.01 grams of sodium chloride is there now. You can use the periodic table. I just went from my experience, and you'll get to that point the more problems like this you do. One thing I do want to illustrate again is this train. Always use this train to cancel out. It makes life a little easier. Grams of mixture canceled with grams of mixture. Grams of sodium chloride cancel with grams of sodium chloride. And your answer is moles of sodium chloride. So 74 times 48 divided by 100 times 58.01. I have to always put my unit, 6.612 moles of sodium chloride. Units. Units, units, units. Mass of 2.6 times 10 to the 23 molecules of ammonia. What conversion factor will you use? Avogadro's number all the way. 2.6 times 10 to the 23 molecules of ammonia. Okay, this is kind of like your pine sol ammonia. It has that pine sol smell. And it's asking for the mass. So mass, I will assume, is in grams. And for every 1 mole of NH3, we have 6.022 times 10 to the 23 molecules of NH3. And for every 1 mole of NH3, I have how many grams of NH3? 17.01 grams of NH3. Molecules of NH3 cancels with molecules of NH3. Moles of NH3 cancels out with moles of NH3. 2.6 times 10 to the 23. So let's put that in our calculator. 2.6 exponent 23 gives you that, times 17.01. Hit that multiplication key, 17.01, and divide that by, I like to put a parentheses here. My denominator is 6.022 times 10 to the 23. And I get 7.34 grams. Able to weigh out if, let's say, ammonia is 100% pine sol, was able to weigh out 7.34 grams of pine sol. Let's pretend it's all ammonia. Then that 7.34 grams of pine sol that I give to you actually contains 2.6 times 10 to the 23 molecules of ammonia, assuming all of that pine sol is ammonia.